So today we are going to start a new chapter, the last chapter, mortality projection. And up until now, all we have studied is sometimes we knew the mortality rate, sometimes we didn't. And most often we calculated the transition probabilities using the mortality rates that were given to us. So we know how important it is for us to know the mortality rate. But again, apart from the questions that we solve, it actually holds a lot of practical importance. So projections for mortality, so based on past experiences, you might try to figure out what is the what likely is the mortality rate going to be for certain kind of people or certain age group of people, or basically whatever it is that you're looking at, annuitants, insurers, or anything else. So sometimes it is very helpful for insurance companies if they can project this mortality rates as accurately, as close to real world as possible. But again, we know that, George Box was the statistician who actually said that all models are wrong. Only some are useful. So I guess we cannot really hedge against 0% error or 100% error, but all we can do is try to do the best possible forecast that we can using all the information that we have up until that point in time. So in today's chapter, what we will study is how do we forecast the mortality rates. So there will be various techniques, mainly three kinds of techniques. So the very first technique that we will study will involve deterministic forecasts. So let me just write here. We are going to study mainly three techniques. The very first technique is known as in general expectation, because sort of what we are doing is people will come, we take experts and they will come and they'll set targets, and based on those targets and basically using those targets, you will try to identify the mortality rate for the upcoming years. And this is deterministic in nature, so this does not vary much. And the second kind of method that we will be studying is Lee Carter. So this is deterministic. And then another one will be Lee Carter. So this will look a bit like a regression, but again, this is very different from the regression. So I'll explain you how is it different. But in general, we'll have mortality rate on the LHS, and on the RHS, we will have some determinants of mortality rates. So whatever is it that helps us to determine the mortality rates for future. And the third technique that you will see is using P-splines. So we have already seen this model before, and both of these are stochastic in nature. So these vary over time. And the fourth method will be of, so these two also come under extrapolation. So here what you are trying to do is you're trying to basically devise something on the basis of all that you have known up until now. So you're trying to forecast something in the future. And again, I think this is the kind of difference that we have, right? Interpolation, something in between, extrapolation, something outside the interval. And the very last is, I guess, explanation. So this can be summarized as explanation. So here, up until basically in these first three methods, we will not look at a particular disease or a particular thing that might cause the mortality to alter. So sometimes if we know, let's say, let us just take the example of the coronavirus. So people must have forecasted the mortality rate for this year, but it didn't quite happen, right, as they might have expected, of course. So they must have revised their estimates. So they must have revised it. And again, I guess, so if you see the mortality rate for people who already have any comorbidity, for them, it must have been increased a lot more than the younger ones. So these kind of scenarios where due to some particular, let's say if a vaccine is developed, or let's say if there is some sort of research in cancer and now people are no longer dying because of cancer because they can be vaccinated against it. So that to account for those kind of changes, you will use the explanation method, where a particular explanation for a particular rate to be either higher or lower will be given, And that will be accompanied by basically if there is research or if there is vaccine or if there is something else which might, basically other than improving mortality, it might deteriorate. So basically mortality rate will increase even more. And that is indeed the deterioration. I mean, that is indeed the bad thing, right? Because mortality in itself is a bad thing. So for it to increase is a bad thing, I think. So yeah, this is like just gist of everything that we are going to cover today. But I think we might not be able to cover all of these 4 techniques today. So we'll try to actually cover only the first and the second one today. And then we can maybe have another lecture tomorrow as well. Tomorrow is a holiday for all of you, right? Is there anyone who does not have a holiday tomorrow? Okay, I'm taking that as a yes. So we'll have a lecture tomorrow. And again, so even before I start with these techniques, see again, here itself in the chapter, they haven't given you anything about the kind of data that we have for mortality. It won't be the case that we will have the estimates of mortality, right? We would have calculated those mortality, right? From the number of deaths observed, from the exposed to lives observed, right? And we've already seen those formulas in the previous chapters, so I'm not going to repeat those. But the data sources that we generally have is generally one is from the population census, and the second, which is mostly used, is NFHS, National Family Health Service. And very widely used is actually sample registration system. So this SRS, and these are actually the kind of data sources that you will use. And mortality rate is actually very important. So sometimes we care about the mortality rate of the whole population in general. But I guess you all might have heard of infant mortality rate, right? Under 5 years of age mortality rate. So sometimes you will have age specific mortality rate. And we will try to take that kind of thing into consideration in Lee Carter model. We'll see how we care about a particular age and how do we expect the mortality rate to behave for a group of people who are of a particular age in general. So just to give you an example, actually, so the mortality rate data has been changing a lot. And people do not normally expect vaccines to be developed, or people do not normally expect any particular research to bear fruit in that particular year. So sometimes the targeted rates that you might have for the next year might not actually be as valid. But again, I guess that is the best you can do. So in case of India, we still need to work a lot towards. I mean, there have been this 17 Sustainable Development Goals, if you all might have heard of it. So one of those is actually to reduce the under 5 mortality rate to as low as 25 per 1,000 live births, and that is the target is to achieve this up until 2030. So, I mean, this is actually very important, not only to developing countries, but also for developed countries. So previously, infant mortality rate used to be very, very high. And then I guess, I mean, because of polio and all of those stuff, and also female mortality rate used to be a bit higher than the males because of those specific reasons that I don't think I need to reiterate. So there have been so many changes and we have progressed a lot. So, I mean, I think I have the statistic here. I usually am not very fond of statistic, but this is a good one. So deaths per 1,000 live births was somewhere around 126 in 1990s. And in 2019, it dropped to 34.3. So that is a very huge improvement that we have done. And we have seen in terms of, deaths per 1,000 live births. So this is not specifically under 5 or infant, but yeah, something that I guess was just nice for you guys to know or be aware of. Okay, so we know that, I mean, there of course are caveats and we need to be careful about the mortality estimates that we project, because if it is underestimated, then it might be lost to the insurance companies, or if we overestimate mortality, then it will be a loss for the pensioners, right? And we've already discussed this again. So what we want to do is neither overestimate it nor underestimate it, because, if you specify or if you basically do not really forecast it that well, then it could cause a financial collapse as well to a company. So it could have that big effect as well. So I would say let us start with trying to project mortality and forecast it using the very first method, which is the method is based on expectation. Yeah. So not much for me to basically add on here, because I mean, this is how some people have actually devised a model, and this is what we're going to use. But this model is very, very important because so again, there have been not many questions. I mean, I only know one question from this chapter up until now in all the past papers, but I would say still, I think maybe that is why I expect that there might be actually a question from this chapter this time, because this is something that is really nice. And in R, I guess you will see how this really plays out nicely. Okay, so first method is method based on expectation. So here we know for sure, once we know the age and once we know the time forward and how much, I mean, in what year do we need our projection for, then basically we will know our mortality rate for sure. So here what generally happens is, this is the formula that they have given. So it looks pretty daunting, but just bear with me for a while. So RXT here is actually nothing but just a reduction factor. So this reduction factor here is your RXT. And again, remember, this is not reduction rate. This is reduction factor. So always remember, rate will be, let's say, 5%. So if I'm talking about a stock price today, which is let's say 100, and if I see a 5% increase, so if my rate is 5%, then what will be my factor? Anyone? It will be 1.05, right? So factor is what I multiply to my x t, let's say, to get xt plus 1. So my xt plus 1 will be 100 times 1 plus r, or 100 times f. So if you are looking at rate, this is how you have. And if you're looking at a factor, factor directly gets multiplied to whatever it is that you are looking for. So here, if I'm looking for the mortality rate, then if I'm calling this as my reduction factor, so if I multiply this reduction factor to my today's mortality rate, I will get my tomorrow's mortality rate. If this t here is, let's say, 1 year, and 1 year is the unit of time that we're looking at. So that's clear. But again, here x represents age and t here represents the future year. So not necessarily always this t will represent a year. Sometimes this might also represent the difference between the years, or how much longer in time you're looking forward in future from today to forecast for. So yeah, so you'll have to guess that by the kind of method that we're looking at. So in methods based on expectation, where we are using reduction factor, T denotes a particular future year. All right. So here I have RXT being equal to alpha x plus 1 minus alpha x times blah, blah, blah. So here alpha x is nothing but the ultimate reduction factor. And now when I say ultimate reduction factor, it means that my RXT can never go below alpha t. So this particular number here is always positive. This can never be negative, right? And that is why that is the only reason my alpha x is the ultimate reduction factor. But again, there will be some adjustments that we will do such that your alpha x indeed becomes, I mean, this is how they have framed the equation, so that your alpha x becomes the ultimate reduction factor. And you will have a particular benchmark, right? That your mortality rate will never go below this particular level and will never be reduced by this particular factor or more than this particular factor. So this is the ultimate reduction factor that you can ever observe. And the proportion of total decline expected to occur in n years. So this might take a bit of a time for you guys to even understand what this means. But for now, I want to skip what SNX means, because I think this is much more explained clearly in the example that we will see now. So let us just assume that this is the formula. So remember, T is what? T is the year that we are projecting for, and N is the total number of years. Okay. So N years is the total number of years. So here the question is, identify the value of the reduction factor when T takes the value of 0, N, and goes to infinity. And you have to describe the amount of reduction in future mortality that is predicted by this formula in each case. So let us assume that T is 0. So now we have just substituted, instead of T upon N here, we get 0 upon N, which is nothing but just 0, right? So if you have anything raised to 0, that is nothing but just 1. So remember, this will be 1 minus alpha x and plus alpha x. So all you get is 1. And now if your T is 0, what does it mean? We aren't looking in future at all, right? We're still in the present. So reduction factor for any age x and time 0 will always be 1. I mean, that is what you would expect, right? It shouldn't change at all because you're looking at the same year. All right. So now we'll go in the next step, which is N. So where my T is equal to N. So I'm looking for all the years that I can look for. So here my power becomes 1. So now if I have a 1 here, you might be tempted to write, just cancel this alpha x and alpha x, but no. Remember, this 1 minus alpha x is multiplied to this particular number here, or whatever that is. So we'll have alpha x plus 1 minus alpha x. So this is for the 1. And then you multiply all of this with the minus of this thing, which is why you get minus of 1 minus alpha x times fn x. And this alpha will cancel. And this is what you will be left with. So now this will actually help us to understand fn x in a much better manner. So here we have already assumed that alpha x is the lowest possible value that you can ever observe for your reduction factor, right? So again, to just give you guys an example, if I say that my reduction factor is 3%, then basically, so let's say if you had 100 deaths per 1,000 live birds, now you will have 97 deaths. So how many number of deaths you were observing previously was 100, and now you will observe 3% less number of deaths, so 97%. So here again, remember, in the very first scenario, reduction rate was 0% and reduction factor was therefore 1%. So here now, if I'm looking at basically my alpha, which is the lowest possible value, if I subtract 1 from it, I know that I get the maximum possible reduction that I can ever observe in my future mortality rate. And that is what gets multiplied to my fnx here. So basically here what it's saying is that your reduction factor is nothing but 1 minus the maximum amount of reduction that you can ever observe multiplied to fnx. And if we go to the previous explanation of what our fnx is, it is something in proportion, right? So here if you have a look, it represents the proportion of the total decline expected to occur in n years. So basically here we know that up until n years, there will be some sort of a decline going on. So if we care only about t years, this fnx represents the proportion of decline that would have happened up until t years out of this total of n years. And here you have that thing multiplied by 1 minus alpha x. So again, the formula just predicts that a proportion. So this proportion of the maximum possible reduction, which is 1 minus alpha x, and that is what we will have as a reduction factor. So again, remember, this is not reduction rate, this is reduction factor. And now, if we have a look at this t going to infinity, we know for sure that this particular value is less than 1. So my fnx is in between 0 and 1. And if I subtract 1 from it, and if I raise it to something which is infinity, I know that for anything number between 0 and 1, if I raise it to a higher and higher number, I get a lower and lower value. And that is why if I raise it to infinity, I'm ultimately going to get something which is almost equivalent to 0. So this second term becomes 0, and all you're left with is alpha x. And that is what you will have. So if you see that you're projecting way, way, way long in future, then also your rxt can never go below alpha x. So that is how this equation will actually tell you that alpha x is the lowest possible value of the reduction factor that you can ever observe. So again, remember, this is not reduction rate, this is reduction factor, because this is very, very important. So now you guys must question that if I want to project my mortality rate in future, let us say I use this formula, okay? I want to project my mortality rate for T years in future, and this is my base mortality rate. So again, you cannot basically forecast mortality rate directly. You will have to consider some base year upon which you will perform some operation, whether you expect it to reduce or not, and then you will basically forecast your mortality rate for the period in future. So let us say if you try to use this particular formula, now you might question, how do we get the value of RXT? Because we will know the value of QX0. This will be given in our table booklets, and that is our base year. So we always consider base year as something which will not be, not a great representative. So it should be a very good representative, and there should be a possible connection that it has only been reduced or increased by a certain factor and not by any other influence. I mean, not by any other influential variables, I would say, or significant variables, I would say. But again, you would see that this method is not actually that foolproof. So you will study another methods, but this is really easy and straightforward. So now here, to figure out RXT, we need to know the values of alpha x and fn comma x. How do we know these values? So this is one of the disadvantages of this particular approach. So you will actually have to gather experts who know things about mortality a lot better and are studying, let's say, epidemiology or something. If you are into that, then you will allow them to forecast these values for alpha x and fn comma x. So let us say if your n is 20 here, as they have chosen in this particular example, these values, so we are looking at this particular age, and these values will be forecasted and basically calculated by experts in their field. Based on what, you might question me again. So alpha x and fn comma x is actually calculated on the basis of, again, the base year. So now you see another disadvantage. If at all you expect there to be any discrepancy in the base year table, then that will be carried forward in these targets. So these are actually what they think is going to happen in future. So they set a target for alpha x and fn comma x, and on that basis, you will figure out the value of your reduction factor, which will then allow you to figure out your mortality rate. So here, I guess it's very important for us to sit and read this particular paragraph. So let me just go through it. So here we have this particular alpha x and this particular f20 comma x for each of these different ages of people that we can have in our study. So whenever I'm saying that my alpha x here is 0.304, what I meant to say is that my mortality rates for people aged 70 will never reduce to below around 30% of the current mortality rate. Again, only for people aged 70. So I'm not talking about any other group of people. Only the group of people who are aged 70. For them, I know for sure that my mortality can never reduce below 30%. And that is why you see that you can only observe a reduction of 70%, right? There will be no, so here when they're talking about 70%, this is about the rate. This is about the rate. But remember, my R in itself is a factor. So when I'm talking about percentage, this automatically denotes rates, right? So again, whenever I have my alpha x, it just says that, I mean, if I have my alpha x value as 0.304, it says that this is the lowest possible value that you can ever have for your reduction factor. And at that time, your R will be just equal to 0.304. And that is what they mean to say here. And now if you come to this particular number here, 0.498. So if we approximate this particular number to, let's say, 0.5, what we mean to say is that out of all the reduction that we expect to happen in 20 years, we expect 50% of that reduction So basically my n is 20 right here. So what I expect to say is when I am writing fn comma x, that 20 years, for the very first 20 years, I expect 50% of the reduction to have already happened. And that is what is conveyed by fn comma x. And if your x is 70, then yeah, for the people aged 70, the 50% of the total reduction that they will ever see is going to happen in the first 20 years of their lives. I mean, the first 20 years after 70. So not like 0 to 20, but from 70 to 90, let's say. So that is how you will interpret these values of alpha x and f of n comma x. And now once you know these values, you can easily figure out your value of reduction factor. So here for the example, they have just taken this is alpha x, this is 1 minus alpha x, and this is 1 minus fn comma x. And here all you need is Q70 20. So 20 upon 20 gives you 1. And this will be your answer. So whatever value you will have observed for Q70 will actually get multiplied by 0.653. And that is the reduction factor that you see. So if you see, I mean, basically now if you have to figure out, so again, remember what kind of question this is answering. Reduction factor will answer the question, how much is your mortality reduced? And if I'm talking about rate, that will answer by how much is your mortality reduced. So now if let's say for the same question, I were to figure out the rate at which I've observed a decline in my mortality, right? What will that be? How will I figure that thing out? Anyone? Would anyone want to guess? So basically what you will do is, whatever the thing you have seen in future minus past upon past, right? So this is what you will do for the same thing. You will do the same thing here. And for future, you will have this thing. For past, you will have minus Q70, 0. And upon, you will again have Q70, 0. So this will just be 0.653 minus 1 upon Q70, 0. Right? So that way you will see that actually, it will be negative. So you know for sure that there have been a improvement in the mortality rate. And by how much? By 35%, because 1 minus 6.5, approximately, it's going to amount to 35%. Any doubts with this? Anyone? Anyone? No? Okay. So now let us try to solve a nice question that they've given us here. So using the values of alpha and f given above, calculate the reduction factors and hence the projected mortality rates for these shaded areas. Okay, and let us see how can we do that. So we'll need help of this particular table, but again, forget that. Let's just try to do it without those numbers. We just need to know whether we know how to do it or not, right? So what all information do we have? So as we know that the reduction factor is just 1 for this particular case in the year 1992, we know for sure that that is our base year, right? Oops. Can you guys hear me? I think there's some internet issue.
Yes, ma'am, we can hear you.
You can hear me? Okay. But I guess, can you guys see what I'm writing? I don't think so. Yeah, maybe now you can. Okay, so again, just by seeing the reduction factor is 1 here, we know that this particular year is nothing but base year, right? And now we're trying to project forward in future. So here the difference is of 5 years, and here to there the difference is of 10 years, right? So we're trying to project our mortality rates for future. And all we know is for people aged 60, the reduction factor is this much in this year, and we'll have to figure that out for 2002. So reduction factor and then the mortality. So once we know the reduction factor, we can easily multiply it, right, to this or this, anything that you might want to do it to, and figure out the value of your Q. Okay, so now my question is, how will you figure out this particular R here? So the very first thing that one should do is, first of all, you should write what is it that you want to calculate. So always remember we used to write R, X, comma T. So my X here is 60 and my T here is 10 years, right? So I'm looking for 10 years in future. So this is T. And I need to know my alpha and 1 minus alpha and this F of. So again, for 60 years of age, if I go back, you will see this is your alpha and this is your value of F. So again, just trust me with that, and this is what you will get as your reduction factor. And once you have this, you will just multiply that with your Q here. So again, because we were looking 10 years forward in future, so if you would have written 5 years, then you would have maybe used this. But because we wrote 10 here, so we know that we're looking at the base 1992. And again, they haven't said that we're trying to project from 1997. Yeah.
Ma'am, I don't understand what R. If R is 1, that's why 1992 is the base year. What if it was 2 or 3 or something else? Then can you just repeat that part?
Okay. So see, what does R mean? R is the reduction factor, right? So when I'm saying that my R is 1, it means that there has been no reduction, right? So generally, whenever you observe your value of R as 1, it is always saying that the rate of reduction is 0 because the factor is 1. So if it was 100 in the previous time, today as well, this is going to be 100. So we are basically saying that there is no change. So we aren't forecasting at all. So we do not expect the mortality rates to remain constant throughout the time. And if you assume that there will be no constant mortality for consecutive years, then if you observe R as 1, then you know that you aren't projecting at all. That is the year that you're looking at itself. So just to give you, so we've already seen that if my T is 0, my Rx0 is always going to be 1. Regardless of what my value of X is. So again, because the base year. So whenever you're trying to project mortality, you always try to base that projection upon some particular year for which you already have some information. And then you try to see whether it has increased or whether it has decreased or how much it has reduced how much do you expect it to reduce in future? Because you do not calculate mortality data firsthand. All you do is you know previous mortality tables and you take those mortality rates and you only see how much do you expect it to reduce or increase. And that is what you multiply to your base year, and that is when you get your forecasts. Does that answer your doubt, Vaibhav?
Yes, ma'am. Thank you.
Very good. All right. So where was I? Yeah, I guess we were trying to figure out this thing. So once we get to our reduction factor, all we need to do is multiply that with our base year. So here Q60, 0. So remember, this is base year. So we aren't projecting at all in future. And that is why we have 0 over there, because T is 0. We aren't forecasting anything. We are still in the present, according to the base year. And when I write R6010, it means I'm trying to see something 10 years down the line. And that will give you Q60, 10, which is this particular number. So we have already filled in this particular blank and this particular blank. So now what about these numbers? So here again, we are forecasting 5 years in future, and we know this particular thing, and we again know the values of alpha and F20, X here. So if we have this, then we can easily figure out using the same formula. So here instead of 10 upon 20, you have 5 upon 20, because we are looking at year 1997 and 97 minus 92 is 5. So 5 upon 20, and these values you get from the table above, and you figure out your value of reduction factor. And once you do that, you multiply that with your base mortality, and you get your projected forecast mortality for people aged 80 years and 5 years down the line. And this will basically sum up your table. So now I want you guys to try to understand what is happening in this table. So if I tell you guys, see, any table will have two particular things going on, right? Anytime we have a table, we have certain thing being represented in rows and certain thing being represented in columns. So here in rows, so each different row corresponds to different ages of people, and each different column corresponds to different years, right? So if you compare, you can compare this mortality rate. So again, we don't care about R, let's say for now. We can care about R as well, but let us say if I'm only caring about the mortality rate now. So I look at this, and I look at this. Do I see any pattern in here? So what do you guys think? Is my mortality rate for 80 always higher than that of 60? It is, right? So every time you see your mortality rate for people aged 80 is higher. So this makes sense, right? Because that is what you would expect. For people aged 80, I mean, they have a higher chance of being dead. Okay, so now let us, I mean, for Q, we already have set expectations. So now let us try to have a look at this R and this R. So one thing you can compare is R after 5 years and R after 10 years. So you want to see whether it increases or decreases. And you can also compare R between the age groups. So whether it increases or decreases across the ages. So if you see here, your 0.843 is actually lesser than 0.928, right? So again, I mean, whenever you have a higher number here, it means that the mortality is higher. So the number that you will get for Q will be higher, right? If you have a higher number of reduction factor here, because that is what gets multiplied to your base Q every single time. So here, if you see, you'll see that for younger ages, which is when someone is like a 60-year-old, the mortality is lower. So the mortality reduces quickly for people who are young compared to people who are old. So this is one conclusion that you can have by observing it across ages. So this was across ages. And now the second kind of, so again, you see the similar pattern over here. 0.714 is also less than, so maybe I should write this. 0.714 is also less than 0.867. So again, the same thing you observe here. And now the second kind of comparison that we can make is across years. So now we will try to compare what happens if you project 5 years and what happens if you project for 10 years. So across years. Now if you see, we observe that 0.843 is greater than 0.714 and that 0.928 is also greater than 0.867. Would anyone like to guess what would this mean? Basically, if your reduction factor is higher for lower years in future, then what does it mean? How do you expect your mortality to behave if this is the case?
Ma'am, I guess a person aged 60 in 2002 will live a longer life than a person who was aged 60 in 1992.
Can you compare those two people?
No, I'm saying the average duration of lifetime.
Yeah. I mean, what you said is actually correct. So again, we are looking at a particular specific age. So you should always be careful when you are seeing your statement. And Weber, we were careful about that. Very good. So we mentioned that we are only looking at, let's say we're comparing the first line, right? So we are looking at the people aged 60-year-old, and we try to forecast. So what we see is that people who are aged 60 in the year 1997 and in the year 2002 have some sort of a difference in the mortality rate. And yes, as Weber rightly said, it is actually more in 1997, which is in shorter period of time compared to the longer duration. So maybe what you can say is that the mortality is decreasing in trend. I mean, the mortality is decreasing in trend, right? So mortality is improving in general. People are getting healthier, right? Because 5 years, because 5 years down the line, people are no longer dying at the same rate as they were. So now if you look at a person who is 60-year-old, he has a less probability of dying than compared to 5 years ago. So that is what it is trying to say. And that is how you will try to interpret these tables. So there should be some care taken about the usage of words with respect to mortality, because when you're saying mortality improves, it does not mean that the value of mortality is increasing. In fact, mortality rate is decreasing, and that is when your mortality is improving in general, right? Because when I'm talking about improvement, it means something good is happening. So people shouldn't be dying at a faster rate, because we consider people dying as something which is not good. All right, so I guess that is how you will interpret this thing, and this is very important. Any doubts with this? Anyone? Any doubts? So again, remember, whenever you are looking at alpha or R, always remember what these are. So the difference between factor and rate, and just keep that in mind. All right. So now here they have just projected the mortality rates for people aged 80. So you see that there is a decreasing trend, right? So the mortality rate is actually decreasing. And again, we are only looking at a particular age, which is 80. And we are looking at 30 years down the line. So from 1992 till 2022. And here in this particular paragraph, they are basically just trying to argue how this particular method might not be suitable. Because the very first thing is that the choice of alpha and F that we have is arbitrary. So this alpha and F will be set as targets by experts, and that will again be based on the previous forecasted values. So it in a way forms a chain, and if there is any particular error in previous one, then it is just getting accumulated throughout the cycle. And it has been observed that if you try to use this method of expectation, then you basically project a higher mortality than the observed rate of mortality. And so, which is generally not the case, because improvements happen, and not necessarily people will die of the same disease that they used to in the earlier years. There might be improvements, there might be, so basically it was, I mean, here they argue about the war, pre-war and post-war, because males used to mostly indulge in cigarettes and smoking and stuff. So they had a higher mortality. But nowadays it is not that higher, because people are aware, and there have been many techniques, and there are changes in the lifestyle and developments, and basically all of the stuff that you can do to not get into the habit. So people do not die of smoking as much as you would expect them to, in at least during the war eras. And that is why if you try to use expectation, then you would be assuming that yes, the chance of a person dying of smoking, let's say, in future is same as it was in the previous years. So you will basically overestimate the mortality. So again, here what the words they have used is that you underestimate the improvement. So again, what does improvement mean? Improvement means a decrease in the rate of mortality, right? And if you underestimate the decrease, then in fact what you're doing is you're over projecting your rate of mortality. You're estimating it at a higher rate than what you would expect it to be at. So again, this is just something that you should be careful about if you're using this particular method. So certainly, yes, this method is easy, but only maybe I would say for like shorter intervals of time, not much more advanced in future. I mean, people say for this COVID year, right? So the last year, the improvements that humans would have expected in the next 5 years were all done in this 1 year. So all the advancement that we might have thought will happen in next 5 years was it was all happened in last 1 year. So you can never really expect what's going to happen next, but all you can do is try your best. And that is why they keep revising this estimate. So it's not like that if you just have a committee which is basically looking at, setting up these rates and all. So they will have to take into various things into consideration. And if such a scenario happens which no one would have forecasted, then they'll certainly sit again and try to revise their estimates so that people can make informed decisions. Whoever might use those data sets, basically. So here they are just asking us to list and briefly describe the various sources of uncertainty involved in the mortality rates projected in the previous question. So again, there will be mainly two kinds of errors. One is the error that you can do when you're trying to project the mortality rate in future. So that will involve basically, what if your formula of RXT is not correct anymore? So the formula that you're using is incorrect. So even though your values are correct for alpha, F, and everything else, if the formula that you're using is not correct, then it is going to have some sort of error, right? So there can be model error. So the way you define model is not actually the way it should have been. So the functional form is wrong. And the second kind of error that you can have is the parameter error. So the values of alpha and F and X, these are subjective, right? People, we call them experts, but they are people, so it will be subjective and you cannot really guarantee whether they'll be 100% correct or not. So there is some uncertainty over the values of alpha and F that we think we ought to use. And then again, whenever we try to forecast, we are saying that yes, we know for sure what the mortality rate is going to be, but we know that there will be some random fluctuations and all of those stuff. And the last kind of error that they're talking about while projecting is again the kind of thing that we talked about, smoking habits. So if there is change in the lifestyle of people, then these will not be the good the previous rates will not be good representative for the next rates. At least if you can figure out how much of people less smoking affects the mortality rate, then you can maybe include that somehow in your reduction factor to take that particular thing into account. And we will do that in the very last method, which is explanation method. So we'll try to see over there, how do we take those things into consideration. So these are the kind of issues that you will have if you want to project your mortality. But again, forget about projection. Sometimes you will have errors in the mortality rates that you base your projection on. So we know for sure that we do not use the crude mortality rates. We graduate them. So even while you graduate, sometimes there can be errors. It is not foolproof. So there will be some random error in observed experience data. Sometimes the data in itself is faulty. And the other times you can have errors while you graduate. So while you try to smoothen it and basically you'll have to choose between smoothening and adhering to the data clearly. There might be some sort of error that you can make while graduating your mortality rates. So again, these are in total the kind of errors that you can actually observe whenever you are trying to forecast your mortality rates. So this is the very first method, which is the method based on expectation. And I think let us just try to actually do a question first. Yeah. So let us try to do this third question. And who would like to read this? Vanshita, can you read this for us? Savri, can you hear me?
Yes, ma'am.
Yeah, can you read the third part?
Yes. The mortality rate for the base year of a mortality projection has been estimated to be N60 equal to 0.006. Sorry.
Yeah, a bit slow. It's slow. Do not rush, because this is like thoda difficult.
It is believed that the minimum possible mortality rate for lives age 60 is 0.0012. It is also believed that 30% of the maximum possible reduction in the mortality at this age will have occurred by 10 years' time. Using an appropriate reduction factor, calculate the projected mortality rate for lives aged 60 in 20 years' time.
Okay. So what do you guys think about this particular question? What all information? So again, to forecast for next 20 years, to forecast what will happen after next 20 years, we will need to figure out the reduction factor, right? So we basically need to figure out the value of R 60, 20. So for that, we will use our formula, which is alpha 60 plus 1 minus alpha 60, which will be multiplied by 1 minus f. What is my n? What do you guys think is my n here? And what should I write in the power of f over there? Anyone? So, okay, very first question. What do you think is my alpha 60 here?
Ma'am, I think N will be 10 years and alpha will be 30.
Alpha will be 30. Why do you think alpha will be 30?
Sorry, 0.3, sorry.
0.3. Okay. What about others? Okay, so first of all, Vaibhav, why do you think alpha will be 0.3?
Because in the question it says 30% of the maximum possible reduction, so that's why.
Is that what alpha is? Is that what alpha says? What is my alpha x? It is the minimum possible value reduction that I can ever have, right? Yeah. So okay, and why did you think that your n should be 10, Vaibhav?
So the 10 years is the period that is given. So the maximum possible reduction would have happened in the next 10 years. So that's why.
Okay. So that is not, I see that you're trying, but think more. What do other people think about this? Okay, what do you think will be my T here? So T is the thing that I'm forecasting in future for, right? So which is 20. I've already written my T here. So 20 upon N. So whatever value I will have for N is what's going to come over there as well. All right. So does anyone remember what is my alpha 60? What does my alpha 60 represent in words? I would like to know that from someone. Anyone?
It is a minimum possible factor.
Yeah, right. Minimum possible
Mortality.
reduction.
Reduction factor, yeah.
Yeah. Okay. So what do we know about here? How do we have some information through which we can calculate our alpha 60 here? Because we certainly are not given the value of alpha 60, right? We see some rate which is 30%. Yeah, but that doesn't mean that it corresponds to our alpha here, right? So because it also says that 30% of the maximum possible reduction in mortality at this age will have occurred by 10 years time. So what does it mean? It basically means that your F 10, 60 is 30%, which is 0.3, right? So maybe if I can write it over there. this particular line tells me that my f 10 comma 60 is 0.3. Okay, but now I also need to know the value of alpha to figure out my value of reduction factor. How can I do that? What is some information given in the question? I mean, there is one information given in the question that we haven't yet used. Which information is that? Anyone? Anyone? Vanshita, are you there?
Yes, ma'am.
Oh, okay. Yeah, good. So, is there any information from the question that we haven't yet used?
M60, 0.
60 comma 0. Okay, yeah, but that is the
M60,
base. Yeah, M60 comma 0. Yeah. But that is the base rate, right? So it will be multiplying that with my reduction factor. Okay. But now to figure out the reduction factor, I need to know the value of alpha 60. How can I know that? Anyone? Keep thinking, try to reread the question again and then see whether you get any clue or not. Are you guys reading the question again? Are you guys there? Okay, Mihir, can you read the question for us again? I wanted to read the third part of the question again.
The mortality rate for the base year of a mortality projection has been estimated to be M60,0, which is 0.006. It is believed that the minimum possible mortality rate for lives aged 60 is 0.0012.
That's
It
it.
is
That's
also
it. That's it. Thank you. So we haven't really used this information, right? That the minimum possible mortality rate for lives aged 60 is 0.0012. Now I've given you guys a hint. We will have to use this particular thing to figure out the rate of alpha. Now you guys think, how can we do that? So I think, see, the minimum possible mortality rate for this particular life is 0.0012, right? And the mortality rate today is 0.006. So what is the reduction factor that you will have here to achieve the minimum possible mortality rate? And that will give you your value of alpha, because even this will be basically just alpha x. So if you rearrange this particular thing, what you get is that alpha 60 is nothing but 0.0012 upon 0.006. And basically this will be, I mean, your mortality rate can never ever go below this, right? Because you know that the minimum possible mortality rate is this thing. And for base year, you have this thing. So the factor, whatever factor you have here, this is the least, I mean, there can be no reduction ever observed lesser than this particular value for this particular example. Does this make sense to you guys? So I know this concept of alpha, F and R. It might take some sort of a sitting and basically trying to do this question and read those paragraphs once or twice. But do you have any doubts now? So remember, what is my alpha? I mean, basically in simple terms, alpha is, you can never observe a reduction in the mortality rate lesser than alpha. That is the minimum reduction that you can ever observe, right? So if you know the minimum rate of the mortality, then you can easily see what factor we have used to achieve that. And that will be your factor, right? That will be your benchmark factor. So there can be no reduction in the mortality rate beyond that particular rate. So lesser than that particular number you will never observe. And any doubts, anyone? Yes or no? I would like to hear a yes or a no.
no, ma'am.
No, ma'am.
No, ma'am.
All right, perfect. So let us now move to the second kinds of method that we want to study today, which is the method of extrapolation. So in this particular method, we have two different kinds of methods. But again, even before we study different kinds of methods, let us try to see what all we can do using this. Did I click on explanation? Yeah, these are expectation, extrapolation, and then explanation. Yeah. So yes, these are statistical models, and in this particular kinds of techniques, we'll be studying two different methods. One is Lee Carter and the other is Peace Splines. So again, these are not actually two very different methods. You can also combine these two, and we'll see how can we do that. Maybe not today, I guess. It's already 8:17. But yeah, let's try to see. So always remember, what do we try to model for? It is the mortality rate. And here we will be looking at so remember when I said that Lee-Carter model is somewhat like doing a regression, but not exactly like it. So this is where it comes. So here we will be looking at 3 particular factors that we think determine the mortality rate. So 1 is age, 2 is period. So by period, I mean what kind of time you're looking for, 10 years, 20 years, or how much in future you're looking for. And by cohort, so when I'm talking about cohort, this will take into account, if let's say I'm talking about pre-war era or post-war era. So all you will do is you will group all the people who were born in the, sorry. So you will group all the people who were born in the same year, and you will somewhere down the line, you think that there is some common factor. There is some factor that affects the mortality rate of all the people who were born in the same year. So maybe if you're looking for a person aged 60, 10 years down the line, and again a person aged 60, 10 years down the line, but the first person was born in year 1999, and the second person was born in year 2001, then you would expect their mortality rate to differ. And that kind of effect is being captured by cohort variable. So just think of age, period, and cohort as 3 different variables that will determine your rate of mortality. So just revising once again, previously whenever we used to write about the central rate of mortality, we only used to write mx, right? But now as we know, it also depends on t. So you will have mx comma t, because if you think it depends on age and if you think it depends on time. So again, if you think it will depend on cohort as well, then you will have a C here. So mx comma t comma c. So again, if you're looking at 3 particular factors, then we know that we can have 4 different kinds of model, right? One is where you only observe one factor, which is mx, which is what you have seen up until now. Second, if you take 2 factors into account, and then you can have age and period and age and cohort. So we for sure know that it varies across ages, right? There's no doubt that it does not vary across ages. You cannot take this period and cohort. I mean, that would make no sense. So age is one thing that we know for sure affects the mortality. And sometimes you can have period, sometimes you can have cohort, and sometimes you can have all 3 of them. So age, period, as well as cohort. So now there is one thing that you should always remember. Whenever we try to do a regression, we always make sure that all the independent variables that we have on the right hand side do not depend on each other, right? So here, if you see, we have age, we have period, which is T, and we have a cohort, which is C. So now if I talk about a particular person, then I can actually represent my cohort as T minus X, right? So here again, whenever I'm talking about T, this does not mean these many times in future. So here when I'm talking about T, it means that this particular person is aged X in time period T. So in the previous case, we were representing T as the future time period, but here T is the time period at which this person is aged X years. So now if you do T minus X, what will you get? You will get your value, the value of the year of this particular guy's birth, right? So for all the cases where you have T minus X is the same number, let's say 1970, then all of those people will have been born in 1970, right? So again, you can actually see that when will that happen. So for M, 60, 20, 30, for a guy who is aged 60 in 2030, for a guy who is aged 61 in 2031, and so on and so forth. All of these will be born in 1970. But now you see there is a problem, right? Because we have these 3 variables, X, T, and C, but I can rewrite my C in terms of X and T. So you might wonder, why do we need C, right? Because if we can already rewrite C in terms of T and X, don't T and X already take into account the factors of C? But we have already seen, right? Even though I'm talking about a person aged 60, in this particular year, let's say a person becomes 60-year-old in the year 1999, and there's another person who becomes 60-year-old in the year 1972, then you would know for sure that the mortality is higher for the person who was reaching the age of 60 in the year 1972. because most likely war period and that guy must be, you know, smoking and stuff, and lifestyle has been changed now. So people are careful and there have been advancements. Even if you have an attack or something, there is still a chance that you will be alive, which wasn't the case in the previous scenarios. So in the previous years at least. So here you see that even though we have X and T as the same, for both of these people, there is a difference in the mortality, right? Just on the basis of what year these people were born in. So you expect that people who were born in certain year to exhibit certain factors, and for people who were born in certain year to exhibit certain different factors. So to take those into account, you always try to take this cohort variable. But again, it's actually kind of very tricky to add cohort because it requires a whole lot of data to even include cohort. And that is why generally people do not include cohort. They only include age and period. So to see how does cohort use more data, let us try to have a look at this particular question here. So here they have just asked us to describe and compare the data requirements if we wish to produce a table of projected mortality rates for pensioners aged 60 to 100 in 12 years time using the two alternative forms of the two-factor model. So the two alternative forms that we have are one where you consider age and period, and the other where you consider age and the cohort. So now we need to see and check what kind of data do we need in each of these particular types. So very first, let's do age period model. So what do you guys think? We are looking at people aged 60 to 100 and we want to project mortality for 12 years. So how do you guys think? And what kind of data do you guys think we're going to require here? Anyone? Do not try to read the answer. So again, remember T here is actually, 12 year is the projection period. So yeah, 12 years is what you're trying to project for in future. Anyone? So let me try this one and then you guys can think for the next one. So whenever I'm talking about, the data that I will require to forecast. So the very first thing I see is that I care about people who are aged 60 to 100, right? 12 years down the line. So the maximum age I feel is let's say 100, right? And the minimum is 60. So I need data where I have seen people aged 60 and 100 and for long enough time so that I can base my next 12 years of projection on that particular period. So you will need some, so generally the data that you have in the past is known as historical data, and that is in the case of stock market as well. So you will say that you will require some sort of history for the data regarding the mortality rates of people aged 60 to 100. So it cannot be the case that you only have people aged 50 and 40. So let us say if you have only started documenting your mortality rates now, then it is highly unlikely that you will have data about the mortality for people aged 60 and 100 because they might not have even attained that sort of age up until now. So that is one of the issues that you will see in cohort because over there age plays a very big role. So here you will only need some good amount of historical data, good enough so that you can project 12 years in future. So 12 years is not actually a big number. So it's fine. And all you will need to know is that you have data of people who attain the age of 60 to 100. So you need to have that data. Okay. So now let us talk about the next kind of model that you can have, which will be age and cohort. So here we do not care about the period. Here we care about the cohort. So what do you guys think is, I mean, what kind of data do you guys think you will need here? Anyone? So actually this can be a bit tricky. So again, now whenever I'm talking about age cohort model, again, we need information about people attaining this particular ages in 12 years time. But to forecast for what's going to happen in the next 12 years times, we need the same sort of data as historical data, right? So here you will face an issue because for people aged 60, let us just, I think, yeah, so this particular paragraph here actually explains it really well. So here they are talking about a particular example. So a person aged 80 in 12 years time. So we're talking about a person who will be aged 80 after 12 years, right? So we will have some sort of data for that particular person in today's terms and in terms of history. So that person will be 68 today. And we might have some sort of data on people aged 68 today, right? So that is what we will use to project the people who will be aged 80 in 12 years. So project the mortality for people who will be aged 80 in next 12 years. But now let us assume if there is a person who becomes 60-year-old in the next 12 years, then today that person is what? That person is only 48 years old, right? So you might not even have that sort of data because this is pensioners data, right? Many people not even think of retirement by 48. I mean, they're kind of assuming that. So it won't be entirely absent, but the data will be very scant. So you will not have that kind of data set. So that is why if you talk about cohort, then you really need a lot more data than just 48, because even if you look at 48, you can max to max take let's say 10 years of data. I mean, at 38, no one is planning to retire or something. At least not, I mean, you won't have data about their pension this early as well. So they're aged 48 today. I mean, so you won't have enough of the historical data to basically try to project your mortality and base your mortality on. So that is why it is very harder to use age cohort model than it is to use the age period model. But again, this does not mean that there is no effect of the cohort. Indeed, they are smaller, but they are still non-negligible, as we have already seen. So, and again, here they are just discussing that the three-factor model will have a logical problem because your C is nothing but T minus X. So it is linearly dependent on each other. So that kind of creates the identification. I mean, that kind of creates, that can create actually some problem, not identification, but yeah, some problems. So, I mean, there have been developments to, there have been developments to not let that come in the way of our projection. Okay, so now let us talk about this particular method, which is Lee-Carter model. So what happens in this model is, the very first thing that you should observe is, I promised you guys in a way that we'll be having mortality rate on the left hand side, but what you see here is not the mortality rate, but the log of mortality rate. So again, when I'm talking about the central rate of mortality, I'm kind of assuming that I can say that it is nothing but the mortality. And at least if you are looking at the case of age nearest or something, then that would give you the same answer. So you can kind of assume that, if you look at the age next, then, so I think that's not a big deal here. So whenever I'm talking about log mortality, why do I talk about log mortality in the first place? So if you remember the Gompertz graph that we saw the very first time we were trying to study the Gompertz law, we saw that the mortality was exponentially increasing in nature, right? So now if you apply logarithm to the mortality, you will get a linear curve. And that is something which is very nice for us if we are trying to forecast. So we see that instead of forecasting MXT, we forecast log of MXT. And then you can basically raise it to E and get down to your true value of the mortality that you care about. But it is certainly easier for us to work with a linear model than with a nonlinear one. So this is how you convert a nonlinear model into a linear one, and you change your dependency variable, which is MXT, to log MXT. So again, here logarithm is with respect to the natural, with respect to the base E. That is why this is natural logarithm that we're looking at. Okay, so here MXT is the central mortality rate at age X in year T, and here AX describes the general shape of mortality at a particular age X. So we will have a look at what exactly this AX represents. So they've given in the bracket that it is nothing but the mean of the time average logarithms of blah, blah, blah. It seems very complicated, but trust me, it is not. We will see soon. So forget about that for now. It just see that it describes the general shape, basically whether mortality is going to increase or whether mortality is going to decrease, whether it's increasing at an increasing rate or decreasing at a decreasing rate, something of that sort. So general shape, whether there will be a hump, no, and blah, 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 all of that stuff. So now let us talk about Bx and Kt. So if you see, we have A subscript X, B subscript X, K subscript T. So here, always remember that we have two parameters that depend only on the age. So they take into consideration how your mortality, is there any pattern in the mortality through age effect? So it will it will be constant over time. If you change only the time and not the age of people, then AX and BX is going to stay the same. But the third term that we have here is KT, which reflects the effect of time trend on mortality at time T. So again, there is only one single index that we use to forecast and take into effect basically the time trend. So how much is your mortality likely to alter based on the time that you are looking at? So that will be reflected in KT. And the very last term that we have is epsilon x comma t. So again, these are independently distributed random variables with mean 0 and some variables that you can estimate. So this is essentially, even though you write x comma t as subscript, this does not depend on age and time. This is independent of age and time. So you write x comma t just to say that this corresponds to the error of mx comma t. So all the effects that are not captured by age and the time will be captured by this particular epsilon here. And again, remember, this actually has a regression kind of a framework. But if you see Bx, Kt, Ax, and Ext, we do not know any of these values, right? So there is no observable quantity on the right-hand side that we generally observe in a regression. So let us say if you're looking at the ice cream sales, you have a documented sales, right? So you are kind of using that observed quantity. So here we haven't observed any of these, and that kind of creates some issue. But again, here, just remember the fact that your alpha x, the AX here, represents the overall age effect on mortality. And I'll tell you why it represents the overall age effect on mortality, even though you still have BX down there. But if you combine this Bx and Kt term, it jointly captures how your age-specific mortality rates evolve over time. So I will try to get into details about this particular model. So let me erase this particular thing. So here, if I take expectation on both the sides, and I will get here is, so you just raise it to E and you take expectation. So you will get that this particular error term has expectation of 0. So in expectation, your MXT is nothing but E raised to AX plus BX KT. But you don't know the values of BX, KT or AX. So again, actually the formula that we have seen is not identifiable. And when I say not identifiable is that when you try to solve for these values of parameters AX, BX and KT, you are not guaranteed a unique value. So you can have multiple different values for BX and KT giving you the same answer. So you will not get a unique representation. And that is one of the reasons why you impose these constraints. So you basically say that the summation of your KT should be 0. So on an average, your effect of time trend on the mortality is 0. And your summation of BX should be equal to 1. And just to give you guys an example, let's say, so with KT, generally this is observed. So let us say this is KT and this is T. We know that summation of it should be 0, right? So let us say this is the place where my y-axis takes the value 0. You will observe that KT is usually linear in nature and it decreases with time. And why does it decreases with time? Because so again, we are kind of assuming that as and when we progress more in time, mortality rate improves. So people are less likely to die than in the previous years. So I don't know how much years in future we can actually say this, but at least now we see that, people do not die at 60, 40 or 50 anymore. I mean, not in that big numbers that they used to in the previous century, let's say. So yeah, mortality is actually improving with time. So if you see your KT, which is the time trend factor, it should ideally reduce as and when your time increases, right? Because then only your mortality rate will be reduced, because KT is something that you add to figure out the mortality rate. So it makes sense for us to draw a downward sloping line. And again, I'm assuming that I'm looking at a linear one, but this is not kind of always expected for this particular model. But yeah, this is what we are assuming, that it meets 0 at exactly in the between of this time. So this is the median time that I'm looking at. So this is my forecast time. And this is all the values of KT that I observe. I will have 1-to-1 cancellation for all of these. So that in median, I have 0. So I mean this and this and this, and all of these will basically cancel each other out. So if you have these numbers and this will be positives and this will be negatives, right? So this number will be cancelled by this, and this will be cancelled by that number. So again, we'll see how do we use this particular concept and this particular constraint. And if you assume that your summation of KT is 0, and again, so one thing we should also think about BX, right? So I forgot to say, but if I assume that my mortality rate should, basically my mortality rate is improving over time. So if I'm talking about improvement, I know that my mortality rate is decreasing in general. So I've concluded that my KT will decrease linearly over time. But what about BX? So as we know that as and when you increase in age, then your impact of the time trend on that particular age also changes. So it is shown that the time trend is less effective on people who are elder, and it kind of affects more for the people who are younger. So your BX will be, so as and when you increase your values of ages, so as and when you increase your value of X, the absolute value for your BX will be decreasing in nature. And because now we have made these two assumptions, there is something that we can say if we have this particular thing. So let me just scroll down. And yeah. So again, in Lee-Carter model function, KT is decreasing over time. And now they have said that at ages below 68, BX values are positive, and at ages above 68, BX values are negative. and they satisfy the overall constraint that your summation of Bx is indeed 1. So now they're asking us to explain how does this particular time period in mortality differs between the two ages. So we have already seen that the thing that we add up together is Kt times Bx, right? So if your Kt is always decreasing, then you know the only difference that's gonna have in mortality is because of the value of Bx. So Bx is positive if you're looking at ages below 68, and Bx is negative if you're looking at ages above 68. So how do you think this will affect the mortality rate? Anyone? So the general argument that they make here is a bit difficult to see and understand, but what you can do is maybe have a look at this particular example. So when I'm saying that my Kt is decreasing in T, it means that if I increase my T, my Kt should decrease. So I will always have a negative term here for my T variable, for my T that denotes the time. Okay, so now if I go back to this particular thing, what happens is if you have a positive value for Bx, then your mortality rates will reduce over time because of the whole thing being negative. And here your Bx, Kt will become positive and it will be increasing function of T. And that is why your mortality rates will actually increase over time. Any doubts with this? So because the negative and negative will kind of cancel each other out, this is the opposite. So if you're looking at positive Bx, then your mortality rates will reduce over time. And if you're looking at negative Bx, then your mortality rates are increasing over time. So this is in general what you have. But again, now, so this was about Bx, it's more than Kt. And the reason why we have summation of Kt being 0 is also to make this particular thing possible. So if you look at the average values of your y variable, which is log of mxt, so you sum it up across from 1 to n and you divide it by n. You substitute the value of log of mxt, the expected value, you ignore the error term here. Ideally, you should not ignore the error term. So here we are ignoring it. So ignoring the error terms. And this is what you get. So again, if you assume that summation of kts for all of the t's is 0, then this basically becomes 0 and this n will cancel each other out. And all you will be left with is this particular ax here. And again, we are looking at n years. And that is why if you basically, you can say that, you know, on an average, your value for log of mortality rate is ax. And again, this happens at the median point. Why? Because I'm looking at the average value of log of mx, right? So again, you expect this to happen in the median when your kt actually takes the value of 0. So we always assume that the median of kt is 0. Okay, and that is what we're kind of looking at. So, in other terms, you can actually, just kind of assuming that this holds. So we have ignored the error terms, which we should not. But if we assume that this is all true, then you can just use e raised to ax as your projected mortality for a particular age x. So that is what we are going to assume, and that is what forms the basis of our next example. So here they have just given us the projected rate of mortality for 40 years in future, different ages, age 60, age 70, and age 80. So you see the mortality rate is higher for higher ages, and you see the rate at which these decrease in future is not same. So and the curve is steeper for 80, and the curve is less and less steeper for the lower and lower years of age. Okay. So now again, in this particular example, we're assuming that your Kt decreases linearly from 1.5 at time 0 to minus 1.5. So you see it starts and it ends at the minus of the where it starts. So usually that is how we assume it to be true. So that in between So let us say we're looking at till time 40. So in the middle of the time, let's say around 20, KT value will actually be 0. And that is where you will see that your projected mortality rate is actually equal to the one that you get here. So here, whenever you will be looking 20 years down the line, you'll see that. So now let us say we have M60, T to project, right? And we have seen that this is the formula. So you will have e raised to A60 plus B60 times KT. And you substitute in the values of A60, B60, which is again given to you. And what is this? This is KT's formula, which was hidden. So yeah, we have this KT formula here, and that is what you will write here. And basically now all you need to do is change the values of T and you will get your projected rates of mortality. So we try to do that. We do it for 0, 10, 20, 30, 40 years down the line. And as we have already seen that when we are looking at the 20, what do we see? We see that this takes the value of 0.00910, which is exactly what we have here. So you see, when I said that my projected mortality rate for when my KT takes the median value is equivalent to just e raised to alpha x, e raised to ax. And that is what you observe here. So again, similar thing you are going to observe if you look at M70T. So for 20 years down the line, you see it is 0.02872 and exactly right. That is exactly what you see over there as well. So again, in this particular example, we are assuming that KT is linear in time so that each age group changes at its own exponential rate, right? So here, if you see the particular rate of change for each of these is e raised to minus 0.018. So for every one increase in time, this particular mortality rate will be multiplied by e raised to minus of 0.018, which kind of represents that there is approximately 1.8% of a decrease because I mean e raised to minus, so decrease, that's why. And why is that the case? So again, whenever I'm looking at the linear, it is something like this, exponential, it is something like that. So you should always remember the connection that we have in between the exponential growth and the linear growth. So we are looking at powers in exponential growth, so like 2 to 4 to 8 to 16. But in terms of linear growth, we are adding terms. So 2 plus 2, 4 plus 2, 6 plus 2, 8 and so on. But in exponential growth, we multiply terms, right? So 2 times 2, 4, 4 times 2, 8, 8 times 2, 16 and so on and so forth. So that is what will that is what's happening here. And again, for the 70 case, you get the same thing. And this is basically, so now you can kind of conclude here based on this particular factors of E. So if you see for 70, we multiply them by the factor of e raised to minus 0.015. And for 60, we multiplied by the factor of e raised to minus 0.018. So you see the number is higher in this particular case, but because we are looking at the negative of the numbers, the number is higher for this particular case. And that is why all we can say is that the higher the value of Bx, which it is for the case of 60 here, the greater will be the effect of time trend. So again, in this particular scenario, it is going to decrease by more. So yeah, the percentage reduction is smaller than that for M60, T, since B70 is less than B60. Does this make sense? I said the correct thing, right? So yeah. So basically each year you reduce it by this thing, and so basically by 1.8% per annum, and over here you reduce it by 1.5% per annum. So that is why your B70 is less than B60, and thus you see that the effect is greater in case of B60 for the time trend and whatever that time trend effect might be compared to the case of a person aged 70 at the same time. Okay, so now again, all we need to, when we try to forecast is the values of these particular three parameters that we have, right? A, B, and K. So this is, we don't really have this thing in much of depth, so I'm not going to cover it, but there are two basic methods that you can use. One is where you can easily derive the value of your AX on the basis of this particular assumption. So you will just take your mortality rates that you have from the past, logarithm and take average of all of those, and you will get your value of AX. And then to figure out the value of BX and KT, you will have to use something which is known as singular value decomposition. So it kind of basically creates two orthogonal metrics. I think I shouldn't even get into that because even though I mean, there's a whole 2-hour lecture that I can take on this singular value decomposition. And there is something analogous to this, which is principal component analysis. So yeah, in short, so whenever I'm looking at something, so let's say if I have a particular stock. So let's say if I'm looking at, a stock which might get affected by certain factors, what principal component analysis will do is it will give me different components. So the very first bar will be, so it always decreases in nature. You will see some histograms. I mean, this is how I remember it when I studied. So you will see some histograms and each of decreasing height than the previous ones. So, and each of those histograms will correspond to each of the different components and each of the different variables that affect your dependent variable. And on the y-axis, you will have how much of importance this holds. So again, if you see that time factor affects a lot more, then you will have your time as the first component. So these components are actually arranged in a particular order, which also matters a lot, because they'll be arranged in the decreasing order of their importance in trying to predict whatever it is that we're trying to. But again, forget about all of that. If you do want to get into that, you can let me know and I can show you I can just share various things with you if you want to get into the depth of understanding how this SVD and PCA works. But yeah, I mean, PCA is actually a very cool concept. So, I mean, that is the concept that people use to teach a machine how to recognize that this particular thing is a cat or this particular thing is a dog. So what happens is, I don't know if you guys have played this game or not, but on Google, I think there is some game where you can draw stuff. So there is some AI. I'll put the link in the Google Classroom if you just want to do some time pass and take some break. You can try doing that. So what it does is basically you have this some yellow and white background thingy on the Chrome and you can just draw. So AI will give you a particular hint and let's say it gives you a book. So you will have to draw that book in 3 or 5 seconds, something like that. And then that AI will guess what that is. So basically it is something like that. And if you try to do that, you will also see how it was drawn by other people. So usually it is not that easy. And sometimes the AI will guess, even if you draw one line, it will start guessing. So let's say if you're drawing a fan, then you draw two V's, so it will guess a V or it will guess, something, I don't know, whatever looks like a V or something. So yeah, it will start guessing immediately. And sometimes it does guess correctly even before you draw the whole thing. So it's very surprising the power that these algorithms have in today's time. I think there's actually a very nice YouTube channel called 2-Minute Papers, which has all of this sort of thing. I mean, that was the place, that was the channel where I first got to know about deep fakes. And I was so terrified, but I was just happy that I'm not yet famous enough so that people can use that against me. But yeah, whatever. I think it's just scary but like what all people can do these days. But yeah. So yeah, I mean, people actually, so what researchers will do is they'll click as many pictures of cats and as different possible pictures in different possible angles and different possible kinds of cats that you can ever have and show it to a machine and tell them, yes, this is a cat, this is a cat, this is a cat, this is a cat. This is not a cat, this is not a cat. It has a picture of dog and a rabbit. They'll tell the machine that this is not a cat, this is not a cat. and the machine will try to see the similar features. The machine will try to see if there is any pattern, and that is what they will have registered in their algorithm. And then whenever you show them a picture, they will see if that pattern exists or not, and then they will guess whether this particular thing is a cat or a dog. So people say that, there are certain animals that do not look like cat but belong to cat family. So yeah, I mean, people do try to trick machine and stuff, but yeah, I mean, we are like way ahead in terms of the technologies these days. All right. So the second method, which is whatever, I think this is in R, some package known as generalized nonlinear models, which is actually super cool. So I really like nonlinear models. I mean, that was one of my optional subjects that I took during my master's, but we didn't kind of study these kind of nonlinear models. It was way different. So you can, so if you try to use that package, it may not necessarily satisfy these constraints, but you can do some adjustment to make it satisfy. So I guess, yeah, that's it. But again, now whenever I'm trying to basically, so once we have these values of KT, BX and AX, all you need to do is try to figure out the next value, right? So using the values of today, you will try to figure out the values for tomorrow. And the only values that change for tomorrow is K, because that is the only thing that depends on time. My AX and BX do not depend on time. They do not vary with time. So once I know the value of AX and BX, it stays same throughout the time period, but my value of KT changes. So to see what is the next value of K that you will have, people generally use ARIMA models. So here they are using a random walk model with a drift. So for people who might not have studied time series as yet, this is actually something that you will study in time series. So these are known as ARIMA models, where you only look at the first difference of the random variable. So if you see here, you have KT minus 1, which is del KT. And I mean, this is going to create some confusion. So always remember, not every time you look at KT minus 1. So here, because you have something like this, you can write it as del KT, but sometimes let us say if you're looking at, let us say if you're looking at KT plus 1 minus KT, how will you write this thing as? For people who have studied time series, my question is for those people. So I can rewrite this thing as del KT. How do you guys think I will rewrite this thing as? It will be?
Same del KT only.
Del KT plus 1, right? So this will be del KT plus 1. All right. Okay. Yeah. So here if you are looking at this thing as your dependent variable, then in expectation, this will become 0 and this is all you will have. So mu measures the average change. So it is no longer the average KT, but it measures the average change in KT, because all we're looking at is the difference, right? KT minus 1. So again, this error term that we have here is no longer the error term of the actual value of K. It is the error between the actual value and, basically it is the error of the difference of the actual value of KT minus of what it was in the previous time period. So yeah, and again, these are independent, normally distributed error terms with the variance sigma squared. So once you have that, in expectation, you can put a hat here so KT 0 will be known to you, but this is what you want to project. So you just add this thing, because on an average, this is how much change you expect in the KT. So you just plus it. So because here we were looking at one time period in future, you only have plus 1 mu. But if you're looking at one more time period, so what you will have is KT 0 plus 2 hat is nothing but KT 0 plus 1 hat plus mu, right? And this is nothing but KT 0 plus mu, which is nothing but KT 0 plus 2 mu. And that is how you get this formula. So you just recursively substitute, and for L years in future, you will have to multiply your mu with L. So shouldn't forget this hat. Yeah. So that is how you get this particular formula. And this is what you will use to figure out your K values for L years down the line. Whatever. Yeah. So now they have a question here, which is Actually, not much difficult, I would say. So yeah, this will be the last thing that we do today. Do not worry. I will will not move forward of Lee Carter. Okay, so just give me 10 more minutes of yours. So now let us say that suppose the last year for which we have data is 2017. The estimated value of K 2017 from the model is 0.93 and for mu is blah, blah, blah. So now you have to predict the value of K 2025. So again, you just use this particular formula that we just saw and you will just substitute in the values of K 2017 mu hat and the difference years is 8. So this is the projection of your K. But again, now this K will be used along with your value of AX and BX to forecast the mortality rate. So I guess that is all that they want to say over there. And now here, so instead of forecasting just one particular value of K, we can always have a confidence interval, right? So that is what they have done here. And here they are just trying to say that again, we have kind of ignored the errors because we are always assuming that we're looking at an expectation. So it will, of course, have that sort of error which we haven't yet taken into account. But the general standard error that you will have is something like this. So your variance of mu hat is actually this thing, sigma square upon Tn minus 1, where Tn is the number of past years data that you use to estimate the value of mu. And now, so if you want to figure out the variance of this thing, this is just a number that you know. So it will become L square times variance of this thing. And thus, if you take the square root of this thing, this becomes your standard error for the forecast. And I hope this is clear. Any doubts so far? So again, here actually the standard error does not represent all of it, and it will actually underestimate the true error. Why? Because again, we haven't taken the actual error of the model into account, which we should have. So we should ideally have a summation of the error terms here as well, but we do not have that. So yeah, there will be some sort of difference. Then here, this is actually just a very simple question. I mean, they've given you the values of sigma, Tn, and you can easily figure out these confidence intervals. So not much, but yeah. So yeah, this will be, I mean, this is how you will write your equation with Hz. And yeah, to try to project L years in future, this is what you will get. And to get the final form of your mortality, just e raised to all of this stuff, and you will get to your answer. But again, this method is, I mean, it has its own advantages and disadvantages. So the very first advantage is that once you estimate the parameters, so once the parameters are estimated, the forecasting is very easy because there's nothing else that you need to do, right? It's very straightforward. And the only thing is that here you can actually know how much of error you have in your parameters that you have estimated. So the degree of uncertainty is kind of known, and you can actually account for that. So that's good. But again, there are certain disadvantages. So the very first disadvantage that they talk about is that this depends heavily on the parameters that you estimate, because that is all there is, right? So if you basically do not have means to figure out the true value of AX and BX, then this whole exercise is in question, right? Because mortality relation might vary over time. So sometimes you might not have smooth enough data. So here they talk about crossover, which is the situation where you have mortality for a person aged 65 at this time lesser than the one aged 66. But 1 year down the line, which I mean, ideally these are the same people, right? So 1 year down the line, if you see, then this person, say aged 65, will have a higher mortality than the person aged 66. So that would create some distortion, and this is not what we expect. So yeah, in some future years, the forecast mortality rate is higher at age 65 than it is at age 66. So kind of, I mean, it varies over time. This relationship should not vary over time. So that is one thing that you cannot, I mean, you cannot actually account for in the normal Lee Carter that we have studied. But again, you can try to smooth the estimates of AX and BX. So the crude ones that you get, you try to smooth them, and then you can avoid this particular thing. So the second is that there is a tendency for these forecasts to become increasingly rough over time. So again, that is also because your AX, BX and KT are, I mean, KT is kind of smooth, but your AX and BX can be rough. So that kind of might lead this forecast to be rough over time. So it doesn't go very smoothly, basically. The third drawback that these people are talking about is that the rate of mortality change is constant over time across all the ages. And this is actually, I mean, there is some empirical evidence that this is not the same. So because we've assumed that, BX is same, so it might not always be the same. So, and then the fourth one is that, again, yes, this does not include a cohort term, where there has been evidence that some cohorts might have improved mortality than the other cohorts. And the last one is that, about the end. So if you try to use this particular model to forecast for something 1 year down the line, then this might produce some jump off effect. So you might observe something which is very, very unlikely to be observed. So these are the disadvantages of using the Lee-Carter model. But again, there are certain extensions that we have studied. So here they are just discussing about the one where you include the cohort effects. But again, if you include those cohort effects, you have the identification problem. And again, you need heavy data. So all you will do is, instead of BX, you will have BX1 and BX2. So BX1 represents the extent to which the time trend will affect the mortality. And here it matters for the cohort. So it will see to what extent the cohort affects the mortality rate. So you have here T, and here you have T minus X. You can also represent, you can also actually change that T minus X to C, to see clearly that you care about X, T, and C, and that's it. So yeah, this is all about Lee-Carter model. And tomorrow we will see how can we actually use the P-splines that we studied in this particular models. So that's all from my side for today. And I think I'll see you guys tomorrow then.